Hello there. Welcome to our today's science lesson. The topic for the day being explaining the three states of matter. In our previous lesson, we looked at the three states of matter, and there's so many issues associated with the three states of matter, how you can try to partially explain how one state of matter changes to another and reverse back to the previous one, or where it has just come from. Give some examples on those states of matter, and also now try to understand using models where we saw the various types of models scientists need to know or to use in their daily life of explaining some aspects that may be a little bit hard to explain. Remember that those things we can be able to explain and use a real example, that this is an example or this is a thing we are doing and it is real, you can touch it. But there are those we cannot be able to explain, but we know they exist, we know they work in a particular way. So in such, we always use the models as we discussed in our previous lesson. In today's lesson, we are still going on with these states of matter, which are three, and we also have some other explanations we need also to make pertaining each of the three states of matter, and I will majorly dwell on gases. I will do some explanation on solids, liquids, but majorly dwell on gases. Now, as we already know, the three states of matter we have are solids, liquids, and gases. In these three states of matter, we also had what we call properties. Properties or behaviors. Properties or behaviors of each of these states of matter. So we have to revisit those properties a little before we embark on some explanation pertaining various conditions. Remember, the explanation we want to do are explanation associated with how the gas or the liquid or the solid will behave in particular conditions. So, some of the properties we noted are solids have a particular shape. I remember having used this one as an example. I can comfortably say this one is round. They have particular shape, cannot be compressed. The particles vibrate in a fixed position, and that's why we have all those properties. For liquids, we say that particles can move around. Particles roll over each other. Because of that, a liquid can be poured, but a liquid cannot be compressed. It cannot be compressed apart from a special one like water, where we say that it is the only one such that it can either be compressed or expanded depending on the temperature, whereby we discovered that, or we learned that a liquid like water at 4 degrees centigrade, it has the highest density because the particles have moved much close to each other, making it much denser, and any other temperature either above or below 4 degrees centigrade, the particles move a little bit away from each other, making it a bit bigger or large, explaining why ice floats on water. But most importantly for our today's lesson is majorly to do with gases. These are a kind of, I can say, a mysterious state of matter that we always see its actions, but sometimes we don't see it unless it is colored. But in most cases, we don't see this state of matter. We only feel its effects. Now, to explain, as I said earlier, I will be mentioning a little of the solid and the liquid, but majorly on gases. So let's start with the solids. We'll look at solids. Solids, the much you can say about solids is about that compactibility of the solids. In the solids, as I've said, particles are close by. Remember what we did in the modeling? When we modeled the solid, we saw that the particles are very close to each other, telling us that there is a high force of attraction between the solid particles. Remember the small solid particles in that particular substance. It can be any kind of substance. So the compactibility of those particles are the ones that make a solid to be identified as a solid, and it will always be in a static position the way it has been shaped. So take an example of maybe a statue somewhere. That is a solid. You will go there today, tomorrow, after a year, 10 years, and it will still be facing you. If it was to face you when you are sitting at a particular position, that is how it will be. Why? Because the particles are meant to be rigid at a particular position, not movable. High force of attraction between the particles, particular shape, vibrate in a fixed position, so that you can always be able to describe it the way you did it yesterday and the way you have done it today, and it's the same way you will do it tomorrow. So for solids, always just look at the particles being close by. Particles are close by, or we can say they are fixed. The particles are fixed. You can also say particles vibrate at fixed position. They vibrate at fixed position. Now, due to this, particles can only be changed, or a substance that is in solid form can only be changed through maybe one physical destruction. So if you are to change this structure which is in solid form, for example that statue, any statue you know of, can only be destroyed by one physical destruction. Maybe there's a bomb, or you take a hammer, sledgehammer, you hit the statue, it breaks. When it breaks, you will still have a solid, but a solid in a different shape. The other way you can do it is if that solid is, or if that substance is made of a material that can easily be affected by heat energy. Talk of a candle. A candle, it is shaped. It is almost something like this. But due to the heat energy during burning, then it will melt, and as it melts, if the contents cannot be allowed to escape, then when having melted, when it cools back to form a different shape. So that's the only way you can change the operation of a solid. Now because of this, then the solids will also have or carry uses based on its properties. They will always carry or be used in particular ways based on its properties. Look at why you should use a stone. We have soft stones that are used in carving sculptures. Why do you go in for that? Because you are looking at the properties of solids, that particles in this solid will be in a fixed position, so they will remain the way I will have left it. If it is a very good, maybe penguin or kangaroo that has been made in a sculpture form, it will always remain that way, because particles in solid are in fixed position. why do you use a tire? And that tire should be made of a particular material. One of the aspects that you looked at was, is the material strong enough, rigid enough to resist the hard pressure that will be pressed or the tire will be working in? Maybe in a very rough terrain, have stones, there is high temperature and all that. The material must always be able to resist that conditions. So you have to go in for a solid. You cannot go in for a gas. A gas cannot be held together to form a tire. A liquid cannot be held together to form a tire. So you'll go in for a solid and so on. Now, if we can look at a liquid, liquids on the other hand, just like solids, we may have some similarities, like a solid cannot be compressed, also a liquid cannot be compressed. But this liquid, since it has that ability of its particles rolling over each other, show me this a particle, this a particle, or maybe I can use these ones. These are liquid particles. They can roll if they were taking this shape. First, they can roll over each other until they change the shape. Now you can see it was raised, but now due to the rolling, they roll over each other and now it is flat. Assuming that these particles could not be able to roll, could this shape be formed? Obviously the answer is it can't. So they do that because they are able to roll. And as they do that, the liquids will always take the shape of the container. The shape of the container. And the container can be an open basket, it can be a tube, it can be anything. So the one thing we have seen is liquid particles roll over each other. Roll over each other. So it is this aspect of rolling over each other that makes now liquids to take the shape of the container. The shape of the container. And that is a very important point of explanation. Because remember, in this explaining, we have always to pick around point of use of that solid, of that liquid, or of that gas. Now I'm talking about a liquid. Where do you think such property can be applied in our daily life? And the point you will commonly see this one being applied is, for example, in a vehicle, the brakes. There is what we call the brake fluid. Brake fluid. A brake fluid, it is a liquid that is being transmitted through a tube. Now, looking at a liquid, because of the property of being able to roll over each other, it makes liquid particles to be transmitted through a tube, any kind of tube. So when you transmit a liquid in a tube, and this one has been made such that it is kind of a piston, which is now a brake pad. Obviously it has a point of pivot point. There's a pivot point here. So when that driver in a vehicle presses on this brake pad, this one will be pushed inside, and since liquids cannot be compressed, this liquid will be pushed towards this other side. When being done that way, we also have another pad that will be this side, and now it will be attached on the rim of a tire. So if this is a rim of a tire, this is the tire. What you will see is the effect of pressure created. There is pressure being created from the inside due to the transmission of pressure from this brake pad by this driver. The brake pad will attach on the rim so strongly, making the tire to stop. What is that? That is an explanation to do with the property of liquids. You are trying to look at how a liquid is. Use its properties to put it to its rightful use. So here we are applying the aspect of one, the particles rolling over each other, which means they move to take the shape of the container, and the container here is the tube. And also you are using the property of particles in liquids, or liquids cannot be compressed. So there is no way you will have to push the liquids to come together, so that there is no effect at the further end. Since there is no compression in liquids, then the pressure you will apply here will obviously be transmitted to this other point. But also put in mind that the tube must be strong enough not to expand. So that one will be looking at the properties of a solid. They will remain close by. So you will find that in so many uses, gases, liquids and solids must always work in one way or another together. Here a solid and a liquid is working together. Maybe the other way you can look at it in terms of liquids, also going by the movement, is when you are mixing two liquids. You have just bought paint. You cannot apply the paint the way it is. You will have to do what we call maybe thinning the paint, lightening it. So how do you thin it, or how do you lighten it? You will have to add in some other solvent. Maybe it can be something like thinner, or it can be kerosene, paraffin, the way you like to call it. But remember, these are two liquids. Those are two liquids. Or maybe you have just gotten ethanol. That is ethanol. And you find it is very concentrated. To dilute this, you will have to add in water. Maybe this one is very common. You have just gotten ethanol, which is very concentrated. We call it absolute ethanol. You want maybe to use it, but not in that concentration. What do? You have to add in water. Which aspect are you applying here? Remember, these are very good application in our life. But for us to be able to explain this, we need to understand the properties of a gas. So, since the particles in ethanol can roll over, and the particles in water can also roll over, so they roll over each other. In doing so, the position that was once held by ethanol particle will be held by water particle, and vice versa. At the end, you will have the two equally dissolved or spread into each other, and you say the ethanol has been diluted using water. Now, just like what we saw in solids, I talked of how you can change maybe a solid, and we said that for solids, maybe you do it physically, destroy it, crush it. But how about for liquids? How can you change a liquid? A liquid, you only apply the issue of rollover. One, change the container. If you change the container, if the container is having a different shape, it will obviously take the shape of the new container. So what I'm trying to say is you can always manipulate the shape of the liquid the way you want, not like the case of the solids. So that's the much we can talk about liquids. Let's look at gases, which is our main point of interest today. gases. Why I've said that this is our main point of interest today is, at least for a solid and a liquid, in one way or another, you have interacted with it so easily knowing that you are doing it. Applications have been done and you can comfortably try to say, surely this is happening this way because these are liquid. You can see it. You can feel it. So for gases here, we have to understand that this is like a mysterious state of matter. Mysterious in the sense that you will always feel, hear, be told, but really seeing it so that you can believe, as we always behave as human beings. In most cases, we want see it to believe. But are you able to see wind? You only see that tree may be swaying around, but you cannot see whatever that is causing it behave the same way it is. You are breathing in. Breathe in, out, in, out. Place a hand in front of maybe your nose or mouth. Continue. You are feeling something pressing on your hand. Repeat it. The same. In, out. What are you feeling? There is some pressure on your hand. Can you be able to explain it? Those are the things I want us to try to explain in our lesson today. So for gases, we need first of all to understand that, though we had already done it in our model, that particles in a gas, using our model, particles are far apart from each other, until we always tend to feel that there is no any force of attraction between the particles. Even if it is there, it is very small that it cannot cause any change. Now, what we also need to understand is that these particles have high energy. High energy. And because of the high energy, we also need to understand that their motion, they move at high speed. High speed, or maybe the best we can say higher speed, because particles in liquids also move. And since they move, in comparison, we have to say in gases, the speed is higher. We also need to realize that these particles, they move. They move in a random way. They move in a random way. So let's first of all explain some of these observations, because they are very helpful in what we are going to talk about next. Now, why do they move in a random way? And why are they moving at a higher speed? All these go to high energy. But where are you getting the high energy? It is because of the high temperature. So what are we seeing? Gases are affected. Gases are affected by one, temperature change. Gases are affected by temperature change. So that's one of the aspects I want us to look at here, and we shall see the applications or by the points of use in our daily lives. So high temperature makes the particles to take in the high heat energy being given in by the high temperature. Remember, high temperature means high heat energy. High heat energy being there, the particles in a gas will take in the high heat energy. As they take in, they obviously now have high energy. And when they have the high energy, now they start moving at higher speed. Just like any other substance, object, even you. When you wake up in the morning, you haven't had your breakfast, you feel a bit weak. Do you think you will move at a good speed as you will have wished? Whether the speed is to do with maybe reading, the speed is to do with walking to somewhere, the speed is to do with running, whichever speed you are talking about, will you do it the same as that other time when you had your breakfast? Obviously not. When you have had the breakfast, it means you have high energy, and therefore your movement will be at a higher speed than the other time when you haven't had your breakfast. Now, the other aspect that we need to understand very well and why is the random way of movement. This is because of as the particles move, as these particles move, let's take this one to be particle number 1 and this one is particle number 2. When this particle 1 is moving towards, let's say, this side, and this one is moving towards the same side, there are two possibilities. One is the two will collide or hit each other. That's not a collision because they are almost moving towards the same direction. Maybe hit each other, and when they hit each other, if they will do it at this point, particle 1 may easily take this other direction, and particle 2 will take this other direction. Looking at the second directions are not even the opposite of the previous one. Now, as they move, this second one will come at this point and hit this wall at that point. After hitting it, it will take maybe this direction. Where is it directed to? This particle. But remember, this one was here, but at the time this one is reaching, maybe it will have also moved it to another direction. So maybe it is this one that will have come and they collide head on. So because of this particle will have taken this direction. Let's look for only two. Move to that, to this, head on, maybe this direction, maybe that, hit the wall, that angle, take this one, hit the wall, that angle, come in, maybe meet another one that was coming. So it becomes a kind of a mess of movement. That mess of movement is what we call the Brownian motion. Brownian motion. Brownian motion, which was tried to be identified in the early years of 1869 that by the scientist Brown, and who gave that motion of particles as Brownian motion. Zigzag way of movement is kind of, there is no direction for that particular particle. But now, that motion takes us to another point. And the point is, when this particle hits this wall at this point, hits this wall at this point, hits this wall at this point, what will be the effect on the wall? The effect is, there is what we call pressure develops. Pressure develops. You develop pressure, what we call gas pressure. What we call gas pressure. Gas pressure is that pressure or that push, not really pressure, but let's use a push as a better way to explain. It is that push. When this particle is coming, it hits on the wall. It will push this wall a little bit, as much as it will turn away to a different angle, to another angle, or directly, but it will have made a push on this wall. That push is what develops to be gas pressure. gas pressure. Now, other things we need to understand to do this gas pressure is, one, when you increase the number of particles, in this restricted container, you will increase the pressure. So increase number of particles. So we are looking at ways on how, as you look at the properties of gases, how pressure can be changed in a container. Pressure can be changed in a container, and the one thing we are seeing here is increase the number of particles in that particular container. But remember, the container must have been restricted, no change of the volume. The other way we can look at it to increase the pressure is reduce the volume of the container. Reduce the volume of the container. When you reduce the volume of the container, but maintaining the number of particles. Remember, this one is now going back to what we talked about when arranging or trying to design your own experiment, scientific reports and all of that you only look at one variable at a time. So these are variables we are talking about. So whatever you learned, you are already applying it. So when you are looking at a variable in terms of volume, then the other variable must be maintained, and that is maintain the number of particles in that particular container, but vary the size of the container. The other way you can increase or reduce pressure in a container is now by varying temperature. Vary temperature. So the aspect of varying temperature is what you have already done here, or we are already explained. By increasing the temperature, you increase the speed of the particles, and by so doing, you now increase pressure, because the particles will be moving at a very fast speed, hit the wall with a high speed, which means do a bigger push, making it to have a high pressure. The other one we need now to look at is increase the number of particles. Assume that this is we have a wall, this is a wall, and I ask one person to come and push this wall at a very long stretch. It's like will not be having any effect on the wall. But add another one, 2, then 3, 4, then 100. If the same amount of push per person is done on the wall, but by 100 people, do you think something will be felt on this wall? Obviously, yes, the wall will fall, because the pressure will be enough to break it and then fall. Then what is that? We are looking at the number of particles. If you increase the number of particles inside this, increase the number of particles inside the container, then it means more particles will be colliding with each other, more particles will be hitting themselves on the wall, and they hit on the walls, they create more pressure, gas pressure, more push, so more gas pressure, making now the walls of the container to be at a very high pressure, that if the material used to make the walls is not strong enough, then you say it will burst. There you will be talking about the number of particles. And lastly, you can talk about the volume of the container. The volume of the container. Look at a foot pump. In a foot pump, we have a piston. You are using this to add pressure to, let's say, a tire. using this to add pressure to a tire. When you push, you pull up, what you are doing is you are varying the volume. You are varying the volume. In fact, it's not just reduce, but vary the volume, such that when you are moving up, you are varying the volume. By increasing the volume, you reduce the pressure inside here. But when you push downwards, you reduce the volume. By reducing the volume, these particles of air that are inside here are forced out. When they are forced out, then they comfortably enter the tire to make it as hard as you would have wished. What you are doing is you are only trying to dance around with the volume. Now looking at the variation in the volume, as you can see, it has been applied. But now we have been looking at how gases can be, or a gas can be manipulated on varying some of these aspects. But it is very good for any one of us, I inclusive, to feel happy by being able to explain where that variation is being applied in our daily life. One of it is already here. I'm sure you cannot be comfortable riding on a flat tire, irrespective of the machine you are using. Bicycle, motorbike, a car, it doesn't matter, bus, but on a flat tire, no. So how would you reverse that flat tire? After you have mended the puncture, you will want to fill in whatever was supposed to be filled in. What is it? Air. How? Using a pump. So if it is a manual pump, maybe you are in a bush somewhere, you can't get that pressure you always use. You now have this one. It will still serve a purpose. But what are you using to do whatever you are doing? You are using that property we know for a gas, that gases can be compressed. You are compressing a gas. Gases can be compressed. That's the application you are trying to use, or that is the property you are using to inflate, to fill in the tire, compressing a gas. Another thing that you can apply when it comes to this pressure of a gas is looking at a car engine. Let's look at a car engine. A car engine has what we call a piston. This is where the magic starts. It has a piston. Several of them if it's a car. Now these pistons are the ones that cause motion of the vehicle. How? When that gas, petrol gas, diesel, whichever fuel you are using, when it is injected in this cylinder, the piston cylinder, so we have the gas, petrol gas, we have a spark plug. We shall be having a spark plug at that point, which sparks. In our daily life, you can say you are just lighting it. Just take a match box stick, then when you light it, what will you see? Petrol will light in an explosion form. The same thing happens in that cylinder. It's only that it is small and it is hidden, you don't see what happens. But at least from the motion of the vehicle, you will know it is happening. So we only work with what you are seeing, the effect. But how it is working, we don't know. That's what we are trying to do. So when this gas is inside here and the spark plug ignites the gas, it burns in an explosion. So in that explosion, in that explosion, it pushes the piston up. How and why? It pushes up because this gas, because of increase in temperature, because of increase in temperature, the particles will want to move with high energy at higher speed in a random way. The same, just like what we did previously. In so doing, the gases will now push on the piston, so many of them at a high pressure. So if the piston was down here before the injection of the gas and before the ignition, then it will be pushed up. So as it is being pushed up, it rotates what we call the crankshaft. It rotates that. And that is the part that will be going to the gearbox and all that until it reaches the tire. When you go for engineering or mechanic, you will understand that better. But our point of interest is just this piston for now. What happens in that piston? The gas gets burned, it expands. And since it is expanding, it will want to take a bigger volume. But this bigger volume has been restricted to one direction, and that is these other sides, sideways and downwards. It is restricted, but upwards it is not restricted. Why? Because the piston can be able to move up. So it pushes the piston up. As the piston goes up, it rotates that. As it goes up, the other piston, which is neighboring, will have lost the gas that was inside to the exhaust. So as it goes out, remember we said that how do you vary pressure? You can talk about increase, or that is vary the number of particles. So by reducing the number of particles by pushing them out, that is in the second piston, the piston will now move down because the particles have been reduced. The piston goes down as this one is going up. So it makes now this one to move up, down, up, down, up, down. Then it transmits the effect through the tire. So you can see the property of the gas here has been utilized properly, looking at the conditions that will make the gas particles behave or do as the properties are saying. So by being able to expand under restricted conditions, it has made the piston to move the way it is moving. And by the piston moving the way it is moving, it has made a vehicle to be able to move the way it does. The other way we can be able to explain this is by looking at an LPG gas cylinder. LPG gas cylinder. Are we able to explain these properties of a gas using that? The answer is yes. When you have an LPG gas cylinder, maybe that is of 16 kgs. Now, that cylinder is normally made of very strong material. It cannot be able to expand. So if it cannot be able to expand, and here you are putting in LPG gas, that is natural gas. This is just natural gas. You remember when we were talking about the Bunsen burner, we can call it natural gas. You can call it methane gas. And if it is in the lab, you can call it a lab gas. But now, the common name we use in our commercial way is natural gas. In chemistry terms, we use methane gas, and in the lab, for all aspects in science labs, we call them lab gas. Now, when you are putting in this natural gas, it is a gas, but you are putting it in a restricted volume. What will happen to that gas? What will happen to that gas? So, this is the opposite of what will happen in the car engine piston. For the car engine piston, it was pushed up. The pressure that was created had to push the piston up. Here, there is no movement of the solid material. So what will happen is the particles will be forced. The particles will be forced to move closer to each other. As you add in more particles, they will have to move closer to each other. Remember, gaseous particles are always far away from each other so that they can have that Brownian motion more comfortably. But here, they are now being forced to move closer to each other because you are still adding in more. Just like where you are seated, if you are maybe 30 in that classroom listening to me, and we now say, let 30 more come in. Have you expanded the room? No. Then bring in another 30. Now you are 90. But you have to fit in that room. You will find that you will start now moving yourself around so that you make sure you allow some small space for the other person to come in. So if you are not liking your friend, you will have to now accommodate your friend by allowing him or her to be much close to you. So if you are far away from one another, meaning that there was no interaction, there was no that attraction between you and the friend. Now that the friend is very close to you, will you not interact with the friend? I'm sure you will. You will in fact maybe even ask your friend, how has been your day? Because you are being forced to. So many of you into the same room. What does it tell us? It is trying to explain one thing. One, gases can be compressed. That's why it has allowed so many particles to come in. But there is one thing that we haven't mentioned, and that is when particles move very close together, because of the high pressure you are injecting the gas into that cylinder, the particles will start attracting each other, and as they attract, they will make the gas to change state from gas now to a liquid. And that's why it is normally called LPG, liquid petroleum product. Why liquid? And yet we know whatever we inject in the cylinder is normally a gas. The answer is in the pressure. As you inject the gas at high pressure, without varying the volume, keeping the temperature constant, but increasing the number of particles, you make the gas to move now from the gas state to liquid state. You can see we are putting these variations constant as we look at one variant, which is the number of particles. So here we have learned another new thing, that when you increase pressure of a gas and maintain the volume of the container, the gas will be forced to move to a liquid. So go home, when you get that LPG container, shake it, and you will feel it is like a liquid is in it. Why you feel it is a liquid is not that it is a liquid, it's a gas. It's only that that gas is under high pressure, so the particles have been forced to come very close to each other until they start interacting, attracting each other. As they do so, they change the state from gas to liquid. But now, when you release, when you press that ball bearing on top so that that gas can go out, what goes out is not a liquid. When you shake, you feel it's a liquid. But what goes out is a gas. How do you explain that? To explain that is the same case. When these particles that have been pressured to be close by, just like you in that room, I've said you are supposed to be 30, now you are a 90 in that room. Then, all of a sudden you are told, now can we have some of you going out? How will you feel when your neighbor who was really pressing on you, making you feel uncomfortable, really pressing on you, very much uncomfortable, that friend now moves out? What will you do? You will now try to feel comfortable in that chair, now that the space is enough for you. The same happens to this. So you will orientate yourself such that the chair and you are more comfortable. So these particles also do the same. When outside that valve, they will now want to take their natural space, move far away from each other. And that's why they go back to gas state and not maintain their liquid state. So that explains why the gas that is in the liquid state in the cylinder is still being used as a gas when in that burner. The other explanation we can also look at is a balloon. Let's look at a balloon. When you have a balloon and you blow in air, you are blowing in air. I'm sure when you are a little bit younger than you are, you used to feel happy playing around with the balloons. What happens when you blow air into a balloon? What you are only doing is, one, you are increasing the number of particles. Increasing the number of particles. Two, this number of particles will increase gas pressure on the walls of the balloon. Gas pressure will be higher because there are more. So many of them will be colliding with the walls. In so doing, they now push the walls of the balloon, making it expand. But why is it that when you blow in, then you hold the balloon, it maintains that size, that volume? It's because the gas pressure from the inside at that particular moment you have just blown in, hold such that nothing goes out, the balloon will maintain that volume. This shows that the pressure from inside will be balancing with the pressure from the outside. Remember, outside we also have air particles. We have air particles, what constitute what we call atmospheric pressure. So the atmospheric pressure, because of the air particles, will also be pushing from the outside. At that moment, the two are in a balance. So you will maintain the balloon at that particular moment. When you still add in more, you blow in more air, it means you are increasing the pressure from the inside. The balloon will also increase in size. But it will reach a point whereby this material for the balloon will be stretching, becoming thinner and more thinner. It will reach a point where it can't expand anymore. At that point, when the pressure from the inside is more than the pressure from the outside, and the material of the balloon cannot hold anymore the pressure from the inside, then it bursts. What does this one tell us? It is telling us that gases can be compressed. And increase in the number of particles increases pressure. Increase in the number of particles increases pressure. And as you do so, the material that is holding the gas can only hold the gas to a particular limit. Beyond that, it will burst. And lastly, let's look at how these gases behave when various gases come into contact with each other. This is the aspect we call diffusion. Diffusion in gases. Take an example. That day you entered your house from school, you are very tired, and your mom was maybe in the kitchen. How did you know that your mom has done something in the kitchen? You are not seeing her, but you feel something has been done in the kitchen. It was the smell of the food that had been prepared. Then how did that smell reach the doorstep of your sitting room? It was because of diffusion in gases. Then how do you explain diffusion of gases using the properties of a gas? The answer is in the movement of the particles. Movement of particles in gas are at a higher speed. And again, particles in a gas are far apart from one another, far apart. So being far away, and air is also gases. Air is also a gas. So the air particles move into the spaces left by the gases, the gaseous product coming from the sufuria. The gaseous product coming from the sufuria mixes with the particles of the air. But these particles are in continuous motion, what we call Brownian motion. So they collide with each other. As they collide with each other, they push each other to other points until the smell covers all the areas it can cover. That is including the doorstep where you got the smell. In so doing, you will have confirmed that the particles in a gas are moving at a higher speed because the smell reaches the doorstep very fast, but also they are in a random motion because when you will move from that point to maybe your bedroom, you will still get the smell and all that. That shows that the movement is in a zigzag manner, or what we call Brownian motion. So as I complete my lesson, we have just been looking at the way the gaseous particles behave in various conditions. The last one being maybe to do with the aroma of food that is normally produced when your mom is working with the cooking pans in the kitchen, producing that good aroma of the food you like, but you meet the aroma at the doorstep. We have also looked at the balloon, what happens in the balloon until it bursts, or if it doesn't burst, but when it is being filled at various steps. We have also looked at the car engine, how you just inject in petrol gas, but what comes out is the whole lorry moving. What is it that is really happening? Is just to do with the issue of compression and relaxation of the pistons. And we also looked at the foot pump that is pushing air into a tire which was flat, and at the end you are happy it is full and you move on. All that is to do with the explanation in relation to the three states of matter that we have been doing, much of it being for gases. These are not the only areas of application or areas of interest one can look at. I give you a challenge of, can you go and identify the various areas you may wish to look at the properties of a solid, properties of a liquid, or properties of a gas for you to be able to explain. That marks the end of our lesson today. Thank you.